You see me on my screen?
We can see your screen. Yep, absolutely.
Okay, we can.
Okay. The first slide, rule-based prediction model, December the 1st outline. Is that what you're seeing? I'm sorry if asking.
Oh, you're good, Gracie. Yes, we
Yeah.
can see that.
Okay, perfect. Thank you. Hi. Good evening, everyone. And so my name is Hugh Han. I go by Gracie. I work in the medical field in university hospital. So I really am grateful that I have learned so much from you and fellow students, Jeff. I'm very, very grateful. So today's topic is the rule-based prediction model. I figured that I would like to apply this to, so I found an article that used rule and tree-based machine learning in COVID-19 prediction, which is in my field. Then among them, they used these models, and then among them, the rule-based models is the QBIST model. So I'm going to talk that after this application, after this article. So this is an article that was published just 2 months ago in one of the distinguishable medical journals. So it's called Forecasting Brazilian and American COVID-19 Cases Based on AI Coupled with Climate Exogenous Variables. So they use two parts. One is the COVID data, which comes from this famous Johns Hopkins dashboard. It's open source database. So they used from January to April in USA, and then the corresponding time in February to April in Brazil. So the predominantly is the past case that is used to predict the future. But interestingly, they also are looking into the climate data. So they obtain these data from the National Weather Service. It's the rationale for the climate data is that it's an exogenous factor that may change the route. So there are articles that said, oh, COVID is a winter disease. We always hear that COVID flu coexistence. But on the other hand, hot temperature may induce transmission, as some other article says. And the reason they chose both, one is they are Brazilian. It's on the different climate planet. In this same period of time, January to April, Brazilian is the opposite. It's in summer, and then so that these two regions are very distinguishable. So here are the heat map of the data. They chose 5 cities which are clustered from USA, California, Illinois, 5 states, Massachusetts, New Jersey, New York, and then also 5 states from Brazil. And the median observation days is around 50 for Brazil and around 90 for USA. So the climate they input are minimum temperature. Excuse me. Oh, I'm sorry. I apologize. 1 second. I'm trying to get rid of this screen, but yeah, I'm trying to minimize the GoToMeeting screen without closing it because it's in my way. I apologize. Anyway, I'm not able to do that. So,
I know the struggle. You're fine. We're fine. You just have to kind of push it away. I have to I deal with this all the time. You just
got it. Thank you.
Grab it and push it away because it doesn't bother us.
I see. Now it's working. Thank you, Jeff. I appreciate it. That makes me see my own screen. full screen. So they have 3 temperature, climate inputs: minimum, maximum temperature, and precipitation. As I said, during that period of time, Brazil has a medium of 25 Celsius, which is very hot. And then the northeast of USA is in winter time. And the outcome, they used 1-day forecast, 3-day forecast, and 6-day forecast. All of them, for all these data, they first use a decomposed model on all of them, and also they did the non-decomposed time series as well, just as a comparison. Then 5 tree and rule-based models were applied: Bayesian regression neural network, QBIS regression, KNN, conditional random forest or quanti-random forest, and support vector regression. So here on the right-hand side is their model. They call it, this framework, recursive strategy. What they mean by that is that first, they obtained the variables, the past COVID case and the climate variables. Then they, then they were decomposed. The lag, they chose a lag equals to 2 based on other people's literature or known framework. So before applying these 5, 6 models, they call it hybrid model, meaning that it's actually what they mean by hybrid on this little circle 3 there. Hybrid meaning that they use the decomposed model plus these forecast model, which is what we learn by standard. But in the medical field, it may or may not. That's why they put it out. And as a comparison, they also did the model applying on the non-decomposed. They just report those giant tables. So that's what they call hybrid model. So after grid search, they apply IMF, intrinsic model function, for each inputs. Remember that there are 2 lags for each inputs, and they are choosing 1-day, 3-day, 6-day forecast, which means 5 lags in total. 5 IMFs were produced. So later, the data is split into training and testing, and IMF is trained within the same model, and meaning that IMF1 within, for example, this QBIS model, the lag 1 is trained within itself and summed up within itself, and then it's evaluated. That's what they mean by same model I've trained. So because they applied 5 models, so there's 5 of these hybrid, meaning 5 prediction plus the decomposed model. And then the model performance they use is improvement percentage of adding extra variables, and absolute percent error, and relative mean sum of error, and of course, because COVID progress, so they can have the real case as observed to compare their prediction. So this graph on the right just summarizes the approach. Here is the formula. The y-hat, remember that they have 1-day, 3-day, and 6-day forecast with a lag of 2, which generates 5 of these intrinsic model functions. So this is a formula for the prediction. The hat is prediction for the cumulative COVID cases of lag 1, lag 2. That's the COVID cases, and that's denoted by Y, and the X denotes the climate variables. So altogether 3 prediction period, and with each 2 lag function produces 5 of these IMFs. So they call it recursive strategy, meaning that all of these 5 IMF are summarized by themselves, within themselves, and all of these predictions are summarized within themselves. So I don't know if it is data science-wise, if it is the right term, but medically that they call 150 scenarios were analyzed, meaning from 2 countries, 5 states within each country. Each of them has 3 forecast period, and the decomposed and non-decomposed with 5 of these tree-based or rule-based models. So together it's 150 scenarios by this recursive strategy. And this table summarizes the hyperparameters of each of the model. The BRNN is measured by number of neurons, and then QBIST, it's measured by number of committees and number of instances, which I will talk in the later. And KNN, number of neighbors, and then conditional random forest, number of randomly selected predictors, and the cost in SVR. So this is an interesting figure. The variable importance by ranking in 2 countries. The light green is Brazil, and then the blue is USA. So, of course, the past COVID cases predominantly outweighs any of these climate variable, both in lag 1 and lag 2. But very interestingly that, especially in Brazil, the climate variables really actually matters a lot. If you compare to the blue bar, which is USA, you can see that their relative weight of past COVID cases are smaller, and their temperature, the maximum temperature, weighs relatively so much higher than the USA. So, and from their model, they're saying that the max daily temperature addition improves some models up to 50%. 50%, that's a significant number. And I don't think that in COVID, all these news and medical advancement, there is enough talk or enough even attention that has been brought to the temperature variables. Overall, they plotted these box plot for all these models. Remember that each of there are 5 states within each country, and the upper panel represents Brazil, and the bottom represents USA. And so that's with the decomposed and the non-decomposed. So on each of the plot, there are 10 of these models. Among all, the QBIST model performs the best, especially in the 6-day forecast versus shorter forecast like 3-day and 1-day. QBIST model really outperforms other model. And I talked about this variable importance in the earlier slide, and also decomposition really matters. It compared to the non-decomposed time series, it gives 70% better accuracy than non-decomposed. Even that this is common sense in data science, but in the early COVID medical journal publications, most of them are non-decomposed. That's why they emphasize this as their advantage. And then next best model among 5 of them is the Bayesian regression model, and KNN performs the worst. So this is, I just highlight this New York region as an example. QBEST, which is here, has the lowest error, absolute error in this case. Interestingly, because they look at each states individually, interestingly that in California, even it's not the QBEST that's performed the best, rather it is the Bayesian regression that performs better, and that's among 5 states. California is the only one that favors Bayesian model, and all the rest of the states favors QBEST far better. We don't know why. And then, so the predicted versus the observed, it's pretty good, but not event-free, especially in New York. In the early days, the prediction versus observed obviously has some deviation. I think that it's probably due to our governor's aggressive intervention, but it stays remain to be seen. So explanation of their current work is that the efficacy of the decomposed model is due to the capacity of the approach to deal with non-linear and non-linearity and non-stationary of the data. And the efficiency of the QBEST model is mainly due to its robust ensemble learning of rules that it takes advantage. On the other hand, the KNN, why it's performing the worst, is probably due to that it requires much more cases. And in this case, they didn't pool of them. They just used individual regions, individual models separately. So the sample size is not enough for KNN. So to illustrate, the author also delineates their future work intend to adopt more deep learning approach, like explaining why Bayesian models works better in California, but QBEST works for the rest of the states. And they will try different decomposition and also multi-objective of hyperparameters. For example, QBEST to twist it further. And they would like to adopt more climate data, knowing that the climate data really matters, actually. So that's an article that I find very interesting. And to go back to the topic today, because last week the tree-based models has been extensively talked about, and that left the rule-based model to be discussed this week. And as this article has shown, that the rule-based model, especially, which is the only rule-based model in this case, QBEST, performs, in this case, better in the COVID prediction than the tree-based model. So what is rule-based machine learning and what is rule? The rules, the definition of rules in machine learning is it typically take an if-then expression. For example, in this red stop sign, if red and article, then stop sign. But tree model also is similar, but rule models differs that the individual rule itself is not a model. Rather, it's any machine learning algorithm typically comprise a set of rules or knowledge base that combinedly make up the prediction model. So unlike the tree-based models, the rules uses ensemble of, they call the rules, and some of the rules can be trees. So rule-based machine learning intend to encompass any machine learning method that identifies, learns, or evolves rule to store, manipulate, or apply. So it utilizes an ensemble of a knowledge, a combination of rules, which is in contrast that any other models, a singular models is usually applied to. And the rule-based machine learning models can include learning classify system, association rule learning, and artificial immune system, and so on. Particularly as example, QBIST. In R, we used as a QBIST model, but it's actually an open source tool. It's a tool for generating rule-based predictive models, and it predicts only numerical values. There are other, it has a sister model that predicts the categorical models, which is beyond the topic today. So it's open source that's developed on the Linux tool, and R just adopted this overall package without just questioning it. And it's up to the QBIST team to maintain rather than the R team. So in specific, a QBIST model resembles a piecewise linear regression model, except that the rules can overlap. And not only it can construct single models, but also multiple models that use this instance-based models, which is nearest neighbors. For example, it can predict annual cost for automobile based on other characteristics. It does it by, again, ensemble of a few linear models together and uses certain criteria, instance and what they call committee, to define. So this is an example of the cubic models in the Linux. So if we just invoke rule-based models without further tuning, it tells you step by step. Rule 1 will have if then as this formula, and then on top of that, rule 2 will apply if then on top of rule 1, and so on and so forth. In this case, it evaluates 11 rules on top of each other. So it's pretty complicated. And on top of it, it can further fine-tune by its so-called committee and instances. So here in the R, there is no formula because it's a QBIST team who maintains the formula, and then R just invokes it as a package. And the Caret package can utilize that, and then just like other tree-based models, it uses the standard X and Y and predict and the resampling and so on. But this is what's really behind the scenes in the cubic model. And I really appreciate your time, and thank you very much. Back to you. Yeah.
Thank you, Gracie. Great, very interesting presentation. So I'm going to turn to the class. Do you guys have questions for Gracie?
Yes, I have a question.
Go ahead, Sean.
Yeah, Gracie, first of all, thank you very much. It was a very detailed presentation and learned something because I'm taking a machine learning course, ML Data 622, which is a pretty complex course, and I mean, I'm not really fully grasping it, but this helped. And I'm going to keep your presentation, that'll help. But question for you.
Yes.
That is, see this ensemble that you mentioned about?
Yes.
The ensemble of various rules?
Yes.
That's one thing. But we heard the word ensemble in the context of boosting and bagging, which is ensemble of different machine learning algorithms. Are they the same ensemble, or they are two different senses in which they are used here?
I think Jeff may answer the best, but I'm trying my best. So ensemble is an English word that means count.
Right. It's a totality of something. Yeah.
So yes, I think bagging, these are the ensemble tools that can be applied to tree modeling. But in this particular case, cubic, even that you don't define anything, it itself is an ensemble of piecewise linear regression. That's what they call, without calling anything else. For example, in your bagging ensemble, you're calling for bagging that ensemble to mechanism to fine-tune your tree-based prediction. But in this rule-based prediction, it itself is not one model. It's a combination or piecewise linear regression of numerical outcome that uses its rules on top of each other, like could be up to 11 rules without calling any ensemble. It's built in, I would say. Jeff, correct me if I'm wrong.
So those rules will be those sort of if statements, right?
That's right. That's what they call it. It's like a step-by-step if.
Okay.
If and then.
Okay, thank you. Thank you very much.
Sure, thank you.
Yeah.
Great question.
Other questions?
Professor, I have a question, maybe to Professor or whoever can take it. So in this type of modeling, are we not losing interpretability of the model? Or if we are able to explain it to our manager, or like what is the fine line where we should take the risk of using this type of model to maybe get a 2% increase our accuracy? Can you give us some insight?
I'd love to answer that question. It's a great question. So here's how I would explain it. Now, one of the things Gracie talked about was the ensemble. Ensemble is basically you mix and match, and you get a little of that, you combine them. Honestly, most of us will never be good enough to create our own ensembles. They're very common in automated machine learning tools, like I showed you guys before Thanksgiving, that did a robot as an example. They're very common in things like that. So in general, you're right, you're losing predictivity, you're losing explainability once you start doing this. But think about this. Have you guys ever studied principal component analysis, PCA? Okay?
Yeah, so yes, a little bit. Mm-hmm.
Can you explain that? There's no way you can explain it. In other words, when I first did my first PCA, I was all excited, I'm like, oh, this is so great. And then I went to figure out what the variables were so I could see what the lift was of the variables to try to explain what they were. And then I realized that they were just made out of the sky kind of new variables that had no connection to reality. Now, they do mathematically, but I can't explain it to anybody at work, right? So now, should I stop using PCA because I can't explain it to my boss? Probably not. If it's worth doing, because what does PCA do for me? It reduces my variables by combining certain things that are collinear, right? Now, it may make up funky new variables that have no meaning in reality, but mathematically it makes my model more simple. And I might get a more accurate model that way. And so that's the trade-off, Farhad, that I got to work on in my mind, right? and I'm using PCA as a simpler example, but it's the same principle, right? Because it's where I trade off is, am I going to trade off explainability for accuracy or for precision or for better fit? That's my trade-off. If it's a couple tenths of a point in R-squared, probably not worth it. If I'm getting some significant lift and each one of those lifts is worth a couple $1 million, darn worth it. That's where you got to sit and work with your leadership and be honest and transparent. We call it transparency at work. I'm going to be transparent with you. I can give you a model that's 82% accurate and I can explain it to the marketing team, or because it's going to be, and some simple rules-based models are actually very explainable. Gracie didn't go into Market Basket, which is another example of one. But if you read the article that I posted online for the optional homework, Market Basket actually makes sense. People buy peanut butter and jelly. You know, there's a combination that you tend to find that you can begin to build trends of this tends to go with this. You know, and so you're starting to set up rules of how these things are combined, come together. So that can build an ability to predict certain things. Hey, if I'm trying to sell something, hey, I realized looking at millions and millions of Market Basket that 80% of people who bought peanut butter bought jelly. You don't have jelly in your basket. I can give you a quick text message and say,